Okay, so we are looking at question 5, and here we're looking at the simple pendulum. So a pendulum consists of a bob suspended by a light inextendable string from a rigid support. This just means that the string doesn't extend at all, and rigid, there's no movement there. The pendulum bob is moved to one side and then released. So basically we've got this situation where you've got your pendulum here, and if that's the vertical position, this is the release point over here. The sketch graph shows how the displacement of the pendulum undergoes simple harmonic motion, varies with time over one time period. Now, we haven't yet done simple harmonic motion. We do that in Unit 4, so this is a bit of an extension. But I won't go through the whole question because some of this question relates specifically to that section. So on the sketch graph above, label with letter A point at which the acceleration of the pendulum bob is at a maximum. Now, the acceleration will actually be the greatest at the two furthest points there, because at that point over there you've got a force due to mg, and you've got another force. Let me use a different color. You've got the tension there, and it produces a resultant force in that direction. Now, as it swings down, at this point over here, we have got your force here, your mg, which is equal to mg there, and then you've got that force over there. These two are in the vertical direction, are actually balancing each other out. There's no resultant force that's actually taking place. It's just the force that is used to cause the circular motion. So at this point over here, at the extremities, you're going to have a max because your force is going to be the greatest at these points. And the reason for that is that force is equal to ma. So where you've got maximum force, you get maximum acceleration. So this would be your displacement where it's in 0 is there. So it starts from there, goes through 0, goes to there, comes back, and ends up there again. So it would actually be these 3 points over here. These are the furthest points. Any one of those, you're going to get a maximum acceleration. And the letter V at a point at which the speed, this is going to be at the center point here, because this is where it accelerates, reaches its maximum velocity at this point, and then it deaccelerates, and at that point over there, basically its velocity is 0. So the velocity is 0 here, velocity is equal to max there, velocity is equal to 0 there. So you would get we should put a V and a V, either one of those 2 points. Now explain why the magnitude of the tension in the string at the midpoint of the oscillation is greater than the weight of the pendulum bob. Because at this point over here, and perhaps I should just redraw this diagram because it's getting a bit messy. So let's just redraw it. So we've got our pendulum, it starts over there, down there, it swings down and it goes to over there. And this is the point where we're actually looking at. We're looking at here at the midpoint. So we're looking at this point over here, we'll call it point A. Now at that point, you've got your mg in that direction, and so your tension must exert an mg to balance that out. But it also has to have a force that causes a circular motion, your centripetal force, and that force is equal to mv squared over r. So we have therefore that your tension is equal to mg plus mv squared over r. Now how do we write that? We've got to write that for 3 points. So we need to state therefore that this is giving me trouble now. At the center point, the bob is accelerating with a force towards the center. Therefore, the tension is equal to the weight plus the force required to accelerate the bob. Alright, so there we have got it. We got his, you see here we've got 3.3 marks, so we've got to basically say, alright, so that the bob is accelerating with the force towards the center, so you get 1 mark. Therefore the tension is equal to the weight plus the force required to accelerate the bob. So you've got your 3 marks there. Okay, now I think we've got enough time. Let's just continue going over the page. We'll go over the page to the next one, the next part of the question. It says the pendulum bob is moved to one side until its center is 25 millimeters above the rest position. Now be careful with this millimeters. That's going to be 0.025 meters. Straight away change that because here we've got this in meters over here. So that's that. Show that the speed of the pendulum bob at the midpoint of oscillation is 0.7 meters per second. So there's meters, we've got to change that into meters. Now basically we're going to use that your EP here is going to equal the EK there, because as it swings down, that EP, that potential energy, is changed into kinetic energy. So we know that the EP, the potential energy, is equal to mgh. So it's that's mgh, and that equals the kinetic energy, which is a half mv squared. Conveniently, our masses cancel, so we have our v is equal to 2gh, the square root. I hope you're okay with that. I just multiplied by 2 on both sides here, times by 2, and then I've taken the square root to get rid of that. So putting that in, we're going to have v is equal to the square root of 2 times 9.81 times, importantly here, 0.025. Perhaps put that into brackets like that. And when you do that, you get 0.7 meters per second. Okay, so we get that. We should write this with 2 significant figures, 7.0, because we are given this in 2 significant figures. Now we here continue. The mass of the pendulum is 0.057 kilograms. The center of the pendulum is 0.8 below the support. Calculate the magnitude of the tension in the string when the pendulum bob is vertically below. So this is what we said before. It's going to equal mg, the weight. So that's equal to mg. And this force over here has to equal mg, to cancel it out, plus it also has to be mv squared over r to provide for the centripetal acceleration. So it's plus mv squared over r. So we just put in our values into here. So we got 0.057 times 9.81 plus your 0.057 times by 0.7 squared divided by the r, which is the 0.8. And when you do all of that, we're going to get our value, which turns out to be 0.59 equals to 0.59 newtons. Alright, fine. So there we have that question over there. Alright, now the rest of the question I'm actually not going to answer at the moment. I will include it in your worksheet for Unit 4, because it's all to do with that section there. So we'll leave that one till later. Thank you very much.